There is a radio network that costs nothing to operate. No license required. No subscription. No cell towers. No internet connection. It sends encrypted text messages up to 10 miles. It works when the grid is down, when cell networks are overloaded, when satellites are unavailable. It runs on open-source firmware that nobody owns and nobody can shut down. And almost nobody in the prepper community is talking about it. I've been running one for 6 months. Let me show you what I found. The technology is called Meshtastic. The hardware is called LoRa. The price of a single node, one device, fully functional, capable of joining and extending a mesh network, is between $25 and $45, depending on which board you buy. I currently have 7 nodes deployed across my area. Total cost of my network, $212. It has outperformed every other communication system I've tested in scenarios where commercial infrastructure was unavailable. That's not a sales pitch, that's a test result, and I want to explain exactly how I got there, because the prepper community deserves better than unverified claims about communications technology. Before I go into the technical details, I want to acknowledge something. Communication is the most neglected layer in the preparedness stack. Everyone talks about food. Everyone talks about water. Power is getting more attention now, but communication, how you coordinate with family across 3 miles of terrain when cell networks are down, how you know your neighbor needs help, how you synchronize a group response to a developing situation, communication is treated as an afterthought. Usually the recommendation is, get some FRS walkie-talkies, store a few, done. That recommendation is not wrong exactly, but it's a minimum viable solution to a problem that deserves a more complete answer. What I'm going to show you today is a system that was designed from the beginning to work without infrastructure, not patched together from consumer devices that happen to work off-grid. Built specifically for decentralized, resilient, low-power communication. Meshtastic is that system. First, the physics. Because the physics are why this matters, and if you understand the physics, you understand why LoRa does what it does. Your Wi-Fi router operates at 2.4 GHz or 5 GHz. Those frequencies carry enormous amounts of data, your streaming video, your file transfers, your video calls. But they don't travel far. Walls stop them. Distance attenuates them rapidly. Go 300 feet with obstacles and you're losing signal noticeably. Go 500 feet with a few walls in the path and you're borderline. The fundamental reason is the relationship between frequency and wavelength. Higher frequency means shorter wavelength. Shorter wavelength interacts with physical objects more aggressively. The signal scatters. It gets absorbed. It reflects off surfaces in ways that create dead zones. The trade-off is fundamental physics, not a design flaw. High frequency gives you bandwidth, but it costs you range. Your cell phone operates at frequencies between 700 MHz and 2.5 GHz, depending on the band and carrier. Some carriers have lower frequency spectrum, 700 MHz band, that penetrates buildings and travels farther. That's why carriers pay billions for low-frequency spectrum licenses. Longer wavelength is more valuable for coverage. But even at 700 MHz, you're dependent on cell tower infrastructure. That tower has power. That tower has a backhaul connection. That backhaul has internet infrastructure behind it. It's a chain, and any link in that chain failing takes your communication down with it. The single point of failure is not your phone. It's everything between your phone and the destination. LoRa operates at 915 MHz in the United States, 868 MHz in Europe. Lower frequency than cell, significantly lower than Wi-Fi. Longer wavelength. The signal bends around obstacles more effectively, a phenomenon called diffraction. It penetrates vegetation better. It travels farther before degrading to noise. The engineering trade-off is explicit and intentional. You give up data rate in exchange for distance. LoRa transmits at somewhere between 250 bits per second and 5.5 kilobits per second, depending on configuration. Compare that to Wi-Fi at hundreds of megabits per second, and you can see exactly what was traded away. But you're not streaming video during a grid-down event. You're sending a text message that says __quote _0 __. That message is under 50 bytes. LoRa handles 50 bytes with ease, across miles, through terrain that would stop your Wi-Fi signal in 100 feet. Let me give you the actual modulation to make this concrete, because this is where LoRa's design is genuinely clever. LoRa stands for long range. It's a proprietary modulation technique developed by a company called Semtech, licensed to chip manufacturers. The technique uses something called chirp spread spectrum. Instead of transmitting at a single frequency, the signal sweeps continuously across a range of frequencies in a chirp pattern. This spreading of the signal across spectrum makes it extremely resistant to interference and noise. The receiver can pull a LoRa signal out of the noise floor even when the signal power is below the background noise level. That's what the spec sheets mean when they describe a link budget of 154 to 157 decibels. You can receive signals that a conventional radio receiver would never detect as distinct from noise. That's why 10 miles is achievable. Not because LoRa broadcasts with more power, it's limited to the same power levels as any other unlicensed device. It's because the modulation is exceptionally efficient at recovering weak signals. Now add Meshtastic. Meshtastic is the open-source firmware and protocol that runs on top of LoRa hardware to create a mesh network. Every node running Meshtastic is simultaneously a radio transceiver, a router, and a repeater. When node A sends a message, it broadcasts on the configured channel. Every node within range receives that broadcast. Each receiving node checks, have I already retransmitted this specific message? If no, it rebroadcasts. The message hops outward across the network, each hop potentially extending coverage by another 2 to 5 miles. Meshtastic limits the hop count to prevent infinite retransmission loops. Default is 3 hops. Configurable up to 7. With 3 hops, you can reach a node 9 to 15 miles away through terrain where direct transmission would completely fail. You just need intermediate nodes spaced within range of each other. Here is the key insight from a systems architecture perspective. In conventional point-to-point radio, your network is only as good as the weakest direct link. If 2 nodes can't reach each other directly, they can't communicate. In a mesh network, there is no single weakest link. If node A can reach node B and node B can reach node C, then A can reach C through B, even though A and C have no direct link. And if node B goes down, the network dynamically routes traffic through available nodes. This is the mesh effect. Self-healing by design. The same principle that makes the internet resilient. Data routes around failures. Meshtastic brings that capability to radio communication in a package that costs $40. Now the real-world test results, because spec sheets are not test results. 6 months of operation across 4 terrain types, all with the same hardware baseline. Heltec V3, stock antenna, unless noted otherwise. Flat terrain, minimal obstruction. Rural area, open fields, light tree cover at edges. Gentle elevation variation, under 50 feet across the test distance. Nodes at ground level. Consistent reliable range, 8 to 10 miles. At 11 miles, I started getting message delivery failures, roughly 30% packet loss. At 12 miles, communication became unreliable enough to be unsuitable for planning purposes. Ground-level deployment in flat terrain is close to the spec sheet range. That is the best-case scenario, and it actually performs as advertised. Moderate terrain, rolling hills, mixed farmland and suburban edge. Elevation variation of 100 to 200 feet. Same hardware. Range dropped to 4 to 6 miles for reliable communication. The terrain interrupts line of sight at longer distances. The signal can diffract around gentle slopes, but harder terrain cuts into the margin. 5 miles in moderate terrain is a conservative and reliable planning number. Dense suburban grid, residential streets, 2- and 3-story buildings, parked vehicles. The kind of urban obstacle course that chokes radio propagation. Nodes at ground level between buildings, representing realistic deployment where you can't always get rooftop access. Range 1.2 to 2 miles. This sounds discouraging until you think about what the mesh effect does with it. In a suburban neighborhood where houses are 200 feet apart, every node within 2 miles of you can reach the next node in the chain. 3 hops in a suburban mesh covers 6 miles even at 2 miles per hop. You don't need individual node range to span your operational area. You need enough nodes deployed densely enough to cover it in overlapping hops. Forest, mixed deciduous canopy, dense secondary growth, moderate hills within the forest. Worst-case scenario for radio propagation, vegetation absorbs and scatters signal, terrain adds obstruction on top of that. Range 0.8 to 1.5 miles. 1 mile in heavy forest is the number to plan around. For a group operating in forested terrain, a rural property with significant tree cover, a hunting scenario, backcountry navigation, you need more nodes, more densely spaced. At $40 each, covering a 10-mile forested corridor with nodes every mile costs $400. $400 for reliable encrypted communication across 10 miles of forest with zero infrastructure dependency. Nothing else comes close at that price point. The single variable that moved the numbers most dramatically across all terrain types: antenna height. I ran systematic comparisons with nodes at ground level, at second-floor window height, at rooftop level, and elevated on a pole. Elevating from ground level to a second-floor window, roughly 15 feet, increased range by 40 to 60% consistently. Rooftop deployment roughly doubled ground-level range in suburban terrain. If you're deploying a stationary node, one that stays in place, potentially solar-powered, put it as high as you can practically reach. The physics reward elevation disproportionately. A $40 node on a rooftop outperforms a $40 node on a table every single time, and the rooftop costs nothing extra. Elevation is free range. I also tested weather resilience because resilience is the point. Rain does not significantly affect LoRa at 915 MHz. The wavelength is large relative to rain droplet size, so scattering is minimal. I ran identical range tests in dry conditions, light rain and heavy rain. Heavy rain degraded range by approximately 8% in the flat terrain test. Negligible. Temperature. Nodes tested from -15 Celsius to +40. Hardware performed within normal operating spec across that range. Battery life decreases in cold. Plan on 30 to 40% reduction at -10 and below, but the radio module itself keeps working. For a communication system that needs to work in winter emergencies, that cold weather performance matters. Now the setup walkthrough. Precision here because precision respects your time. 3 things required: hardware, the Meshtastic app, a Bluetooth-capable phone. Complete list. For hardware, I recommend starting with the Heltec V3 or the LILYGO T-Beam. The Heltec V3 costs $28 to $35. It has a small built-in OLED display showing received messages and node status, useful for field verification that the device is alive and receiving. The T-Beam adds onboard GPS, enabling location sharing between all nodes on the network. Every node broadcasts its GPS coordinates. Every other node can display a map showing the network's geographic distribution. Useful for group coordination in the field. T-Beam costs $40 to $50. Both run identical Meshtastic firmware. Both work well. Heltec V3 to start simple. T-Beam if you want GPS location sharing from day one. Critical purchasing note. Order the correct frequency. 915 MHz for North America. 868 MHz for Europe. The frequency is determined by the radio module soldered onto the board. It cannot be changed in software. The listing on AliExpress or Amazon will specify the frequency. If it doesn't specify, ask before ordering. 10 seconds of due diligence prevents a $30 mistake and a 2-week wait. When hardware arrives, plug into USB to charge. Some boards arrive partially charged. Some arrive depleted. Charge before first use. Download the Meshtastic app from iOS App Store or Google Play. Free, open source, same app for all supported hardware. Open the app, enable Bluetooth on your phone, tap the Add Device button. Your node appears in the scan. Pair it. Default pairing code is 123456 unless previously configured. You are now connected. The node is operating on the default public channel. Messages you send are visible to any Meshtastic user on default settings within range. For a private preparedness group, configure a private channel immediately. Private channel setup takes 30 seconds. In the app, radio configuration, then channels. Set a channel name. The app generates an encryption key, AES 128, the same standard used in banking. Every member of your group needs this key entered into their device. Share the key once out of band, a secure messaging app, or simply in person. After that, all channel traffic is end-to-end encrypted. Nobody without your key can read those messages, including other Meshtastic users operating in range on the default channel. Your private channel traffic looks like noise to them. Total time from hardware in hand to first encrypted message between two nodes. I timed 3 separate first-time setups with people who had never used Meshtastic. Fastest, 14 minutes. Average, 19 minutes. Slowest, 23 minutes, mostly spent on Bluetooth pairing lag on an older phone. The firmware handles channel management, packet routing, hop counting, duplicate suppression, and acknowledgement tracking automatically. Your configuration job is: point the antenna vertically, set a channel name, distribute the key. That's the full setup. On antennas, the stock antenna included with most LoRa boards is a short wire stub or basic whip. It works for testing. For a deployed node at maximum performance, replace it. An aftermarket 915 MHz fiberglass antenna, weatherproof, with a mounting bracket for outdoor deployment, costs $8 to $15. It delivers 2 to 3 decibels of gain over stock. 2 to 3 decibels sounds minor. At the margin, at distance, in mixed terrain, it's the difference between a message arriving or not arriving. At the cost of a cup of coffee, it's the highest return on investment modification available for this system. Replace the antenna on every stationary deployed node. The legality question, addressed clearly. LoRa at 915 MHz in North America operates under FCC Part 15, governing intentional radiators in unlicensed spectrum. The ISM band at 902 to 928 MHz is open to any device meeting power and duty cycle requirements. Meshtastic firmware respects both by default. No amateur radio license required. No commercial license. No registration. No identification. Buy the device, turn it on, operate it legally. In Europe, ETSI regulations govern 863 to 870 MHz under similar unlicensed rules with duty cycle restrictions. Meshtastic EU frequency mode respects those restrictions. The encryption is legal in both jurisdictions. There is no regulatory barrier to deploying this for communication purposes. The answer is unambiguous. Now where Meshtastic fits and where it doesn't. FRS and GMRS walkie-talkies. Voice capable, simple, no infrastructure dependency, batteries everywhere. Range typically 1 to 3 miles in real conditions. No native encryption, no mesh, point-to-point only. FRS belongs in your stack for short-range voice. Meshtastic doesn't replace FRS for voice. Different use case. Licensed amateur radio, massive capability. HF reaches globally. VHF repeater networks cover regions. Digital modes add data, but requires license to transmit, significant hardware investment for serious use, and the repeater infrastructure you rely on still has power dependencies. If the local repeater loses power, that resource is gone. Meshtastic requires no external infrastructure. Satellite communicators, Garmin InReach, Spot. Global coverage regardless of local infrastructure. Genuinely useful, but $60 to $150 per year recurring, message latency of minutes in some cases, and dependency on commercial satellite constellations you don't control. Meshtastic costs nothing per year after hardware purchase. Peer-to-peer mesh apps on phones, Briar, Bridgify. No additional hardware, but range measured in hundreds of feet, not miles. Bluetooth and Wi-Fi don't reach through terrain. Meshtastic's niche, multi-mile encrypted text, no infrastructure, no recurring cost, no license, mesh extending range through automatic relay. That combination doesn't exist elsewhere at this price. This is a real gap. This is why it belongs in a serious preparedness communications stack. Now the failure modes. Every system has them. I'm not glossing over these. Primary failure mode. Social, not technical. The hardware is reliable. The firmware is actively maintained. Meshtastic has been in development since 2020, has a large active open source community, regular firmware releases, and genuine engineers contributing. This project is not going away. But you cannot communicate with someone who doesn't have a node. Single node network means you're broadcasting to nobody. The mesh effect requires multiple nodes. This is a coordination problem you solve before the emergency, not during it. The mitigation is simple. Get the people in your preparedness network set up now. 3 nodes is a functional network. A group of 3 households with 1 node each, spaced 2 to 4 miles apart, creates a working communication path across the area with redundant routing. Minimum viable deployment. You have a node, 2 other people you trust have nodes, and you've tested together at least once before you need it. Total cost across 3 people, $90 to $150. Total setup time, 1 afternoon. That is the investment to go from 0 to functioning group mesh network. Second failure mode, power. Each node needs it. T-Beam has onboard battery for 12 to 16 hours of active operation. Heltec V3 needs an external bank, which is actually an advantage. You choose the capacity. A 20,000 mAh LIFEP04 bank runs a Meshtastic node for 3 to 4 days. A 20-watt solar panel with that bank powers it indefinitely in most conditions. Cost, $60 to $80 for the solar solution. Factor this into permanent deployment planning. A node with a dead battery is not a node. It is a $30 piece of inert plastic. Third failure mode, key management. Meshtastic's AES 128 encryption is strong. The key is stored in the device. If a device is lost or captured, someone sophisticated enough to extract the stored key can read your channel traffic. For most preparedness scenarios, this is theoretical, not practical. But if operational security matters to your situation, and next week's video will explain exactly when it does, have a key rotation procedure. Device lost. Rotate the key on all remaining devices. New key distributed out of band. Fresh channel, 5 minutes. Have the procedure established before you need it. Let me close with what 6 months of actually running this network taught me. I set it up to verify the claims. I keep running it because it works better than I expected. The first time a test message came back acknowledged across 3 miles of suburban terrain in under 8 seconds, I ran it again. Then again from a different location. Then at the edge of tested range. The verification instinct doesn't stop just because the system works. Let me verify that. It kept working. The spec sheet says 10 miles. My terrain says 2 to 5 reliably. I trust the number I tested over the number I was given. That's the number I plan around. The open-source dimension matters more than it might first appear. Meshtastic cannot be shut down by a company decision. Semtech holds the LoRa modulation patent, but the hardware implementing it is manufactured by multiple companies. The Meshtastic firmware is MIT licensed. Anyone can compile it, modify it, distribute it. If every Meshtastic developer disappeared tomorrow, existing firmware continues running on existing hardware indefinitely. No subscription to cancel. No terms of service update that removes features. No company that decides your use case is no longer supported. You have the firmware. You have the hardware. The network is yours. This is the dimension most people are not thinking carefully enough about with their communication systems. The resilience of the communication layer is ultimately determined by who controls it. Commercial satellite subscriptions, controlled by a company. Cell networks, controlled by carriers. In extremis, governments. Licensed ham repeater infrastructure, controlled by whoever maintains the repeater site. Meshtastic, controlled by the people in your network. The firmware is yours, the hardware is yours, the encryption keys are yours. You own this communication system in a way you don't own any commercial alternative. That asymmetry matters when you're planning for scenarios where commercial alternatives become unavailable. If you've set up Meshtastic, and I think more of you have than the prepper community discussion reflects, because this technology has been quietly growing for years, drop your range test results in the comments. Real numbers. Your terrain type, your distance, your hardware, your antenna, stationary or mobile, ideal conditions and worst-case conditions. I will aggregate what comes in from this community and publish the summary. Not a spec sheet summary, an actual dataset from real deployments in real environments. That database doesn't exist in any organized form yet. Let's build it together. The next video is the one I'd been working toward since the first episode. We've audited water, power, food, shelter, medical, and communications. 6 layers of the preparedness stack. Each had a gap between perceived capability and actual capability. Each had a fix. The 7th layer is different. You can't buy it and install it. It's a set of decisions about how you operate, what your information exposure looks like, what happens when you are visibly better prepared than your neighbors and social structures have degraded around you. Security, not alarm systems. The full threat model, including the threats the prepper community avoids discussing because they require uncomfortable conversations about trust, operational discipline, and human behavior under stress. That is next. Subscribe. You've built the systems. Next we find out whether they hold up when it matters. Let me add something I didn't fully address in the setup section because it keeps coming up when I talk to people who've looked at Meshtastic but haven't deployed it yet. The question is, what does the day-to-day experience actually look like? What do you do with it when there's no emergency? because the answer to that question determines whether this technology becomes a practiced skill in your stack or an expensive piece of hardware sitting in a drawer. Here's how I actually use it. My 7 nodes cover a rough corridor about 8 miles across, a mix of suburban and semi-rural terrain. 2 of those nodes are stationary, one on my rooftop, solar-powered, running continuously, one at a neighbor's house, also stationary. The other 5 are portable, in go bags, in vehicles, one permanently at a relative's house 2.8 miles away. On any given week, I send a few test messages to verify the network is alive. Not because I expect an emergency that week, but because the test data is the health check. When a node goes offline, battery died, someone moved it, firmware glitch, I find out during a routine test, not during an actual event. This is the same discipline as running your generator monthly, not because you need the power today, because you need to know the generator works before you need the power. The test protocol is simple. Once a week, I send a message from my handheld node, wherever I happen to be, to the node at my relative's house. I note the delivery confirmation, the hop count, and the approximate time to acknowledgement. I log it in a simple text file: date, location, hops, latency, weather conditions. 6 months of that log now gives me a picture of how the network performs across seasons, across weather patterns, across the variability of day-to-day conditions. That's not obsessive documentation, that's a baseline. Without a baseline, you don't know if your system is degrading. With a baseline, a change in typical hop count or latency is a signal worth investigating. The other practical use is location sharing during outdoor activities. When I'm in an area with unreliable cell coverage, hiking, a rural property visit, any situation where the cell network is marginal, I enable GPS broadcasting on my T-beam. My Heltec-equipped nodes relay my position to anyone in the network. If I haven't checked in by a certain time and someone can see my last known GPS position on their Meshtastic map, that's useful safety information. Not sophisticated, but simple and functional, and it requires no cell signal to operate. The point is, Meshtastic is a system you build familiarity with during normal conditions, so that it's not a new technology you're trying to learn during an abnormal one. Every radio system I've seen fail in a real deployment failed because the operator wasn't practiced with it, not because the hardware was bad, because the person holding the hardware hadn't used it enough to operate under stress. Use it now. Know it now. The emergency is the wrong time to read the documentation. Now I want to go deeper on the mesh network concept because I think most explanations of it understate how significant the architectural implication is for preparedness planning. The standard framing is, more nodes equals more range. That's true, but it's only part of the picture. The more important property is fault tolerance. Consider a group of 8 households using a Meshtastic network spread across a neighborhood. In normal operation, messages route through whatever path has the best signal. Node A might reach node F through B, C, D, E, a 4-hop path. That path works fine. Now imagine a scenario where node C loses power. The house it's in lost power. The battery ran out. Something happened. In a point-to-point radio scheme, that's a broken link. A and F can no longer communicate through that path. In Meshtastic, the network detects that node C is no longer acknowledging retransmissions and dynamically routes around it. If there's an alternate path, A to B to G to F, for example, the network finds it automatically. No configuration change, no manual rerouting, no human intervention required. The network heals itself. This matters enormously in exactly the scenarios you're preparing for. A grid-down event that takes out some nodes while leaving others powered. A situation where some group members evacuate and their nodes are no longer in their previous locations. A scenario where one node's battery management failed and it's offline unexpectedly. In each case, the mesh network's topology adapts. The remaining nodes reorganize communication paths around the failure. This is not a feature you have to activate. It's the fundamental property of a mesh. It is why this architecture was specifically designed for military and disaster response communication long before Meshtastic made it available to anyone with $40 and a phone. The comparison to your other preparedness systems is direct. You build redundancy into your power system, multiple sources, failover between them. You build redundancy into your water system, multiple collection methods, multiple storage points. Communication should have the same redundancy architecture. Meshtastic gives you a communication layer where every node is simultaneously an endpoint and a relay, where the failure of any single node or even multiple nodes does not take the system down. That is the correct architecture for a system you're depending on in adverse conditions. I also want to address a specific scenario I get asked about frequently. What if I'm deploying this for a community group larger than 5 or 10 people? A neighborhood watch, a local preparedness group, a rural community with dispersed homesteads. The scaling properties of Meshtastic are relevant here. The protocol handles up to approximately 100 nodes on a single channel without significant performance degradation. Beyond that, you start to see increased latency and higher packet collision rates as more nodes compete to rebroadcast messages. For most community preparedness scenarios, a neighborhood, a rural township, a small town, 100 nodes is far more than you'll ever deploy. You're not going to have 100 people in your preparedness network. If you somehow do, Meshtastic supports multiple channels, and you can segment traffic across channels to manage the load. The administrative reality for a larger group is, someone needs to be the network administrator. Not a full-time job, but someone who maintains a list of nodes, their locations, their operators, and who is responsible for key management when devices are added, lost, or replaced. For a group of 10 to 20 people, that administrative overhead is minimal, maybe an hour per month. For a group of 50 or more, you need a more formal process. The technology scales. The social organization has to scale with it. One more thing on the community dimension. The Meshtastic project maintains a public map showing active nodes worldwide. Before you deploy, check it for your area. You may find other Meshtastic users already operating nearby. Your private channel is encrypted and separate from the default public channel, so they're not a concern for operational security. But knowing the technology is active around you is useful. Nodes on the public channel extend the reach of the overall mesh for everyone operating in the area. The open-source community around Meshtastic has built something that deserves more credit than the prepper community has given it. Active firmware development, clear documentation, a Discord with thousands of members, a significant fraction of whom are doing real technical work on the protocol and hardware. Satellite message bridging via MQTT, solar monitoring integration, integration with APRS, the amateur radio packet network for users who have licenses and want to bridge to that infrastructure, emergency notification modules. The firmware is not a toy. It's a serious communications platform that happens to run on a $40 board. Compare the development trajectory to commercial alternatives. Most commercial preparedness communication products peak at their launch feature set and receive incremental updates if they receive any at all. Meshtastic in 2024 was meaningfully better than Meshtastic in 2022. Meshtastic in 2026 is meaningfully better than 2024. The open-source development model with a large engaged community produces a compound improvement curve that commercial products rarely sustain. You are not just buying a capability today, you are buying into a platform with an active development roadmap and a community that is genuinely invested in making it better. That is the case for Meshtastic in one video, $40. Open source, legal, encrypted, no infrastructure, no recurring cost. A communication layer you own completely, that operates when commercial infrastructure doesn't, that gets stronger as more people in your network deploy nodes, that heals itself when nodes fail. I have tested it for 6 months in real terrain, and it performs as described. Not spec sheet performance, real terrain performance, with the numbers I gave you to plan around. It earns a place in a serious preparedness communications stack. The comment section is open. Drop your test results. Real terrain, real hardware, real numbers. Let's build the database this technology deserves.